Okay guys, 6-3, solving equations with like terms. Basically what we're going to be doing is starting and having an equation with variables on both sides of the equation. So we're going to have to talk about like terms, what they are, and combining them, making sure that we have variables on both sides, and then we're also going to talk about special case solutions. So let's get started. So for these kinds of problems where the variable's on both sides, you want to make sure you got the variable on one side before you try to undo anything. So make sure it's on one side before you try to undo anything. Now we're going to start with the lesser valued, or I guess the lesser coefficient. And so we have 10q and 8q. 8 is less than 10, so we're going to start with that 8. We're going to minus 8q from both sides. So in a way we kind of are undoing things because it's a positive 8q. We're going to minus 8q. We need to do that from both sides to keep the equation true. So we're using the addition property or the subtraction property of equality. So we're combining like terms. Notice I didn't try to minus 8q from anything else other than a term that has q in it. And then, oh, that's going too fast. And then so we simplify, and we get negative 2 plus 2q equals negative 1. And we're going to combine like terms again, add 2. Notice I'm not adding 2 to something that has q in it because they're not like terms, but regular numbers are like terms with each other, so we're still working with like terms. And simplify, and you get 2q equals positive 1, and finish the rest. And I'm just kind of lazy, so I just wrote my answer as part of my work still, but q equals 1/2, so there you go. Let's try another one. Before we try another example, let's just talk about what the distributive property is. I know you guys have seen this before. If you have something inside of parentheses and being times by another number, so you have b plus c inside of parentheses and then times by a, well, it would make sense that you could distribute that a through, and so a times b plus a times c. But I didn't write that correctly. It's actually, those two statements are equal. And the same goes with subtraction. So I'll show that in just a minute. Let's talk about like terms. Combine like terms if they have the same variable. Now you can have more than one variable, so in parentheses s. But if it is the same variable, it needs to have the same power. We're not going to talk about multiple powers here, just power of 1. So if you see a variable that's the same, you can combine those terms. Let's look at the distributive property with subtraction. You can probably say what it is. If you have inside parentheses b minus c and it's being times by a, then that makes sense that it would be equal to a times b minus a times c. And we could prove that using writing subtraction as addition, but and then just using the real distributive property, but we'll just assume that the subtraction does work. Okay, so let's try these examples. Notice that in example 2, solve and check your solution. You have both sides of the equation you have to use a distributive property. So I like to show that I'm using the distributive property with these arrows. That 6 is going to be multiplied by the 2j and the negative 7. And same with the 1/3 being multiplied by both terms inside the parentheses. And so you get 6 plus 4j equals 12j minus 42. And then you want to look at the lesser value or the lesser coefficient. So which one's lesser? 4 or 12? You have 4j, 12j. You should probably subtract or start with the 4j. You could subtract the 12j, but I like to work with positive numbers personally, so you end up with 6 equals 8j minus 42. And now you're still actually combining like terms. From here on out, you can think of it as working backwards. J is being multiplied by 8 and then subtracted by 42. So we need to add 42 to both sides because we're working backwards. Or you could think of it as combining like terms. So you have 48 equals 8j, divide by 8, and you get j equals 6. So how about the next one? You notice there's no like term, there's no distributive property, but we still need to combine like terms. So I show that I'm going to use the commutative property and move the negative 3y over by the 5y and the 32 over to the side. That's the commutative property. And now I can combine 5y minus 3y, that's 2y. So 2y plus 32 equals 34. Combine like terms, or you're basically working backwards. Y is being times by 2 and added by 32, so I'm going to minus 32 from both sides. I get 2y equals 2. Divide by 2, I get y equals 1. I need to be able to show that I know these work. If I plug in 6 for j, I would find out that I get, let's see, 12 minus 7 is 5. 5 times 6 is 30. And so I better get 30 on the other side. And I'm sure you get inside the parentheses, you get, if I'm taking 1/3 of a number and I'm supposed to get 30, then inside those parentheses you'll probably get 90. Okay, sometimes there's the special cases where an equation, especially when there's variables on both sides, you can have an equation where there is no solution, or meaning no value will make it work, and another equation might have infinitely many solutions, so any number that you put in will make it work. Now, I'm going to have to go through and change this, but that T right there should be a C. Okay, and so otherwise this is a not the same kind of linear equation that we want to work with. So we want to work with the same variable. We don't want two variables where there's infinitely many solutions no matter what, usually. Anyway, so if I have in this first equation 8c plus 7 minus 8c, do you see how those are going to cancel out? And then I'm left with 7 equals 34. And that is not true. 7 does not equal 34. And whenever you get a situation where you have something doesn't equal something else, then you know that there is no solution. And there's a symbol, the empty set symbol for no solution. You can just write there is no solution. There's no number that you can plug in for C that will make this work. On the other hand, sometimes you'll get a situation where both sides seem to be totally equal. So let's do the distributive property. And we get 3t minus 5 equals, 3t minus 5. Now some of you won't notice, but that is saying something is equal to itself. That means that there are infinitely many numbers you can plug in for t to make this work. Well, some of you guys would try to combine like terms, and you'd get that 3t would cancel out, and you are left with an equation that is true. Negative 5 equals negative 5. Again, it's still a true equation. Some of you might try to add 5 to both sides, who knows, and you'll end up with 0 equals 0, which is still true. So if it's a true equation and all the variables cancel out, then we use this symbol, the infinity symbol, to show that there are infinitely many solutions. So all numbers work. All numbers, all real numbers, will make this true. So those are the special cases, and you'll see this every once in a while. You may even see it on the test. So here are my general steps. If you'd like to write these down in your notes, step 1, make sure that both sides are simplified. If you have parentheses, use a distributive property. If you have like terms, combine them. So combine like terms. Use a distributive property. That's what part of our lesson was about. So make sure you do that first. And then step 2, get the variable on one side. And this is always done by adding or subtracting. And I like to look for the lesser coefficient, the value that is lesser. So if one of them's negative and more negative, then I would choose the lesser value, so the more negative number. And then just make sure that you work backwards. Ask yourself what's happening to the variable. So everything else is step 3. Everything else is what we've already learned in 6.1 and 6.2. So just be careful with special situations. Don't ask yourself what is happening to the variable at first. Ask that after you've made sure that you've simplified both sides and gotten the variable on one side. Once you've done that, then start working backward. So, thanks, guys.